Okay, so in the last video, we looked at solving problems that have constant acceleration. And in the video before that, we talked about solving problems involving objects that moving at constant velocity. And so those are the two main types of motion that we're going to see throughout the next couple months, either constant velocity or constant acceleration, or some combination of those two types of motion. Okay, so today we're moving on in our kinematics unit. And to do so, I want to pose this question to you. Is this a true or false statement? Heavier objects always fall faster than lighter objects. Okay, so I want you to pause it here and see what you think. Okay, so the answer to the question, heavier objects always fall faster than lighter objects, is that always true? The answer is no. That's actually false. In fact, as we'll see in just a second, there are situations in which heavier objects fall at the same rate as lighter objects. Okay, and normally I would do a demonstration for you so that you could see that. The reason a lot of people believe, kind of intuitively, using their gut intuition, that heavier objects fall faster than lighter objects is because of what's called air resistance. Okay, and so when you think of a falling object, if there's air involved, or if the object is falling through some type of fluid, like air or water or oil or something like that, then what happens is as it falls, those air particles collide with the falling object and kind of impede its falling. Okay, and so in certain circumstances, the shape of the object or the weight of the object can affect how quickly it falls. Okay, however, if you remove the influence of any air resistance or any other fluidic forces, then what we'll see in these two videos that I'll link is that actually all objects are going to fall at the same rate. Okay, that is the same acceleration. So check out the two videos I'm going to link below. Again, the takeaway I want you to get from these videos is that in the absence of any air resistance, all falling objects, regardless of how heavy they are, fall at the same constant acceleration. Okay, and so hopefully after watching these two videos, you are convinced by that. Okay, so let's get to the notes. Okay, now the situation in which an object is falling only under the effects of gravity, that is, without any air resistance or any outside forces, is what's called free fall. So up until now, in the last video and the practice worksheet that went with that, we were solving problems with constant acceleration for objects that were moving in the horizontal direction, that is, side to side. Okay. However, objects can also experience acceleration in the y direction as well. Okay, so these falling objects, as long as the only thing affecting the falling object is gravity, okay, by definition we say that object is in free fall. Okay, and if we have that condition, okay, that is, if we have a falling object that is in free fall where there's no air resistance, okay, then what we find through observation and experimentation is that those objects fall at a constant acceleration. Okay, now if there is air resistance, and we'll talk about that a little bit later, if there is air resistance, then that object would not be in free fall, and it would not have a constant acceleration. Okay, it would actually have a changing acceleration, and in order to solve problems like that correctly, you would need calculus, and it would be much more complicated to handle. Okay, and so that's why, at least for now, we're going to restrict ourselves to situations where objects are falling in free fall. Okay, now, if an object is in free fall, okay, here, right here, this middle bullet point is the key concept in this part of the unit. Okay, so make sure you take really good notes on the slide. The key concept is this. All objects in free fall experience a constant downward acceleration of approximately 9.81 meters per second squared, regardless of their mass. Okay, now, a couple things. Okay, let's break this down. Number one, all, meaning regardless of the mass, heavier objects don't fall faster than lighter objects, assuming that you're talking about free fall. Okay, constant acceleration is important because we know how to solve problems with constant acceleration. Okay, that's what we've been doing for the past couple days. Okay, that's what we talked about in the last video, is solving problems with constant acceleration. Okay, and so even though free fall seems like a new situation, mathematically speaking, as far as problem solving goes, we're going to use the exact same equations for constant acceleration that we've been using. Okay, now the direction of that acceleration is down. In the last video, I spent a lot of time talking about how velocity and acceleration are not the same thing, how acceleration has nothing at all to do with which way an object is moving, okay, how acceleration has nothing at all to do with how fast an object is moving, okay, or in what direction it's moving. And so when I say all objects in free fall experience a downward acceleration, that does not mean all objects in free fall are falling down. Okay, for example, if I throw a baseball up into the air, even as it's traveling up, okay, its velocity is up, it is still experiencing a downward acceleration due to gravity. Okay, so make sure in your mind you understand the difference between velocity and acceleration, because those are not the same thing. Okay, so when I say the direction of acceleration due to gravity is down, okay, I'm not saying that objects have to be moving down to be in free fall. I'm also, by the way, not going to tell you that that is a negative value. Okay, the acceleration due to gravity, the direction is down. Whether that's positive or negative really just depends on the coordinate system that you define. If you define a normal coordinate system, okay, I say a normal coordinate system, whereby up is the positive direction and down is the negative direction, okay, then in that situation the acceleration due to gravity would be negative. However, there is absolutely nothing to stop you from defining a coordinate system where down is the positive direction and up is the negative direction. And in that situation, the acceleration due to gravity would be positive. Okay, so the direction of the acceleration due to gravity is always down. Whether that's positive or negative really just depends on your coordinate system. Now, I will also say that the value 9.81 meters per second squared is an approximate value, and it actually changes on different parts of the Earth. Okay, so actually as you go higher up from sea level, the acceleration due to gravity value decreases. In some parts of the world, it can be 9.80, 9.79, 9.78. In some places, I've seen textbooks in some parts of the world give a value of 9.82 instead of 9.81. Okay, so that 9.81 value is only an approximate value. Okay, now for purposes of IB questions, there's situations, okay, many situations in fact, in which you can use a value of 10 rather than 9.81 meters per second squared. Okay, the IB allows you to do that on multiple choice questions when you're not allowed to use a calculator. For the time being, just to make the math easy in this class, we're going to use a value of 10 meters per second squared for the acceleration due to gravity rather than 9.81 meters per second squared. Okay, technically speaking, this is the value that you would use on free response questions, and this is the value you would use on multiple choice questions. Just for now, okay, just for this semester, and maybe even next semester, we're going to use g equals 10 meters per second squared as the magnitude of the acceleration due to gravity. Okay, that symbol g, again, is the symbol for the acceleration due to gravity. It is an acceleration, and again, an object in free fall is only falling under the effects of gravity, and so it would have that constant downward acceleration. Okay, so g is not 10. Again, the sign just depends on the coordinate system that you define. Okay, so hopefully you took really good notes on that slide. We're going to get into solving some problems with free fall. Again, we're going to do 2 examples before we finish this video. Okay, so problem solving with free fall. Here are just some things to consider. Okay, the first bullet point is basically a repeat of what we talked about on the last slide. Okay, now, in situations when you're throwing an object up into the air, okay, I want you to consider what is the velocity of that object at its maximum height. Okay, so imagine an object being thrown up into the air. It goes up, 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 and at its highest point, think about its motion at its highest point. Okay, the object stops moving at its highest point. Okay, why does the object start moving at its highest point? Because at its highest point, the very next thing that happens is that the object begins to fall back down. Okay, so in other words, it changes direction. Okay, so the velocity of the object at its maximum height would be 0. Okay, now I should be careful. I should really say the velocity up and down of that object at its maximum height is 0. Okay, because in the next unit we'll see, well, we'll get to that in the next unit. Never mind. Okay, so let's just say for now that would be v equals 0 meters per second squared. And I'm telling you this because this is often a context clue to solve certain types of problems. Okay, so by definition, at its highest point, the object has to stop moving. Okay, if it was still moving at its highest point, then, well, that would be the maximum height, right? Because then it would have kept going up. Okay, now the second point I want to point out is when an object is thrown upwards, what is the acceleration of that object at its maximum height? So see if you can figure this one out. Okay, when an object is thrown upward, what is the acceleration of that object at its maximum height? Okay, and the answer to the question, assuming that the object is in free fall, of course, is that the acceleration of the object, if you define a coordinate system whereby up is the positive direction, then the acceleration of that object would be negative 10 meters per second squared. Because if it's in free fall, then it would be under the effects of gravity, and it would be accelerating with a constant downward acceleration due to gravity. Okay, and the magnitude of that acceleration is 10 meters per second squared, and the direction is down. And so if we define up to be the positive direction, then down is the negative direction, and that's why that negative sign is there. Okay, and so if you said the acceleration is 0 at its maximum height, then you're still confusing velocity and acceleration. Okay, make sure you clearly understand the difference between those two things. Velocity has to do with how fast you're moving and in what direction. Acceleration has nothing to do with how fast you're moving or what direction you're moving. Okay, the acceleration tells you how quickly your velocity is changing and in what direction your velocity is changing. Okay, not what direction you're moving in, what direction your velocity is changing in. Okay, and finally, the last question to consider, when an object is dropped, what is its initial velocity? If you imagine holding something in your hand, okay, holding it out to the side and opening your hand and letting it go, how fast is it moving as it leaves your hand? Okay, and the answer to that question is 0 meters per second. Okay, now you can definitely throw something down, okay, but if you just drop an object and you're not given any more information besides that, okay, then you can assume the object begins to fall with an initial velocity of 0 meters per second. Okay, then it's going to accelerate down due to gravity. Okay, so just keep those problem-solving tips in mind. Okay, so now we're going to do two examples solving problems with free fall. Okay, so example 1. Example 1 says a ball is dropped from rest off a 15-meter high building, and there's a few questions. Okay, first question says determine how long it takes the ball to reach the ground, and the second question says determine the velocity of the ball right before it hits the ground. So just like any kinematics problem, I start by identifying my given information. Okay, the fact that the ball is dropped, now it says it's dropped from rest, but even if you took out the from rest part, that's a context clue telling me that my initial velocity is 0 meters per second. We just talked about that on the last slide. Okay, now it's dropped from rest off a 15-meter high building. Okay, so let me draw a picture of the situation. So let's say I drew it as a cliff, but just pretend, this is the edge of a building. And the building is 15 meters. Now I need to define a coordinate system. And so I'm going to make my coordinate system like this. I'm going to say that this initial position where the ball is dropped, I'm going to call that yi. Okay, for my initial y value, I'm going to say that's 0 meters. And then the ground is down here, and I'm going to say that's going to be y equals negative 15 meters. Okay, because it's falling down. Now, why is it negative 15 meters? Well, because clearly if the height is 15 meters and I define my coordinate system so that the top of the building is 0, okay, then when it's fallen down 15 meters, it's 15 meters below where it started from. That would be a position of negative 15 meters. Now, I didn't have to define my coordinate system like that. Okay, I could have said that the ground is 0, and then the initial position would have been 15 meters. Okay, and I'd get the same answers no matter what. Okay, and if you're not convinced of that, try it out for yourself. Okay, so I have implicitly defined a coordinate system whereby down is the negative direction, because if you look, traveling down moves me from 0 to negative 15 meters. Okay, so I'm looking for time. That's given, or that's what it says in the question. It says determine how long it takes the ball to reach the ground. My displacement, S, is going to be negative 15 meters. I'm just going to rewrite my givens over here. The negative sign is very important, because if you don't have the negative sign, you're going to get the wrong answer later on. And I have one more given. Okay, because it's a free fall problem, I automatically have a given for free. I have that the acceleration, okay, is caused by gravity. Okay, so the ball is in free fall, there's acceleration due to gravity, and that's 10 meters per second squared down. And because of my coordinate system, okay, I am going to say that is negative 10 meters per second squared, and that is my acceleration. Now, I choose the equation that has those variables in it. That equation should be the one that says S equals ut plus 1/2 at squared. I go to plug in. Okay, I have negative 15 equals 0 times t. I don't know what t is. Okay, so I just leave that in there. Plus 1/2 times a times t squared. Okay, notice that the squared is only applied to the time. And now I simplify. Negative 15, 0 times t is 0, so that whole thing goes away. Over here, half of negative 10 is negative 5. I divide both sides by negative 5. And negative 15 over negative 5 equals 3. And then my last step is to take the square root of both sides. I do not leave my answer as a square root, okay, because the square root has an infinite number of sig figs, and I don't want that. That's bad. Okay, that's too much precision. Okay, so I'm going to round it to 1.7. I'm going to write 1.73. Really, it should probably be 1.7, but just to include an extra sig fig, 1.73 seconds. And that's the answer to the first question on example 1. So pause it there and make sure you write all of that down. Okay, notice by the way, if I had put 15 instead of negative 15, then I would have been trying to take the square root of a negative number. My calculator would blow up at that point and say, something about no real solutions, because the square root of a negative is, of course, imaginary. Okay, now the second question says determine the velocity of the ball right before it hits the ground. So I'm going to erase some of this. And my givens are not really any different, okay, but my unknown is, okay, because now instead of looking for time, I'm looking for velocity. Okay, so now my new unknown is v. So now I want to choose the equation that has s, u, v, and a in it. Now, technically speaking, could I just go back in and use this time to do the calculation? Yeah, sure. I could do that, but just for fun, I'm not going to. So I want the equation that has those variables in it. I look at my list of equations. This is the one that you would be using. Okay, I get a plug in. This is 0 squared plus 2 times negative 10 times negative 15. I get v squared equals, okay, so that is 150 times 2, that's 300. And then I take the square root of both sides. Okay, now using this equation, I'm just going to tell you, this doesn't come up too often, but something that you need to know about is when you use this equation is kind of stupid. And what I mean is, if you look at this equation, it's solving for v, right? But you can't ever get a negative by taking the square root. So what happens if your velocity is supposed to be negative? Because here, my velocity should be negative. If you think about the situation, the ball is falling down, so my final velocity should in fact be negative. Well, in that situation, you just have to tack in the negative on your own. Okay, so it should be negative 17.3 meters per second. The equation will give you positive 17.3 meters per second. The negative sign you have to figure out on your own, okay, because it makes sense in this situation. Okay, that's a situation where you just need to be smarter than your equation. Okay, so pause there if you need to finish writing that down. Okay, and let's take a look at one more example. Okay, example 2 says Mr. Walker tosses a stone up into the air. It leaves his hand with a velocity of 4 meters per second. The first question says when the stone has risen to a height of 0.5 meters, what is its velocity? Okay, so first of all, I toss a stone up into the air, it leaves my hand with a velocity of 4 meters per second, and then after it leaves my hand, it's going to travel up, right? It's going to travel up to half a meter. That means that this velocity right here is going to be my u. Okay. So u equals 4 meters per second, that's my initial velocity. Now let's think about this in terms of coordinate system. So let's say I'm here, and let's say my hand is here, and let's say I toss it up into the air half a meter. I'm going to make it so that this is y equals 0 meters, and I'm going to say that this height is at y equals 5 meters. And so again, I am implicitly stating that up is the positive direction. Of course, you're free to choose any coordinate system you want, and you would get the same answer. Okay, so this is the coordinate system I'm going to use. Not 5 meters, 0.5 meters. That means that the displacement of the stone is going to be 0.5 meters. Because it's traveling in the positive direction, 0.5 meters. Now I'm asked about the velocity, so v is my unknown, and then the acceleration, because the stone is assumed to be in free fall, and because I have a coordinate system whereby up is the positive direction, that is going to be negative 10 meters per second squared. I choose the kinematics equation that has those variables in it, okay, and that is going to be v squared equals u squared plus 2as. I'm looking for v. I have u, so 4 squared plus 2 times negative 10 times 0.5. I simplify. Okay, 4 squared is 16. Okay, 2 times negative 10 is negative 20, and then half of that is negative 10. So I get v squared equals 16 plus negative 10, which is 6. So v is going to be the square root of 6. And I'm typing that into my calculator as I write that down. It's going to be 2.45 meters per second. And the direction, because remember this equation you have to account for the direction on your own. Should the direction be positive or negative? Well, it should be positive because the stone is going up, right? And so that's the answer to the first question for example 2. Now, on your own, I want you to see if you can answer the second question. How long does it take the stone to reach its highest point? Okay, so pause it here, see if you can answer that second question. How long does it take the stone to reach its highest point? Okay, and hopefully the answer you got is t equals 0.4 seconds. Okay, if you did not get that, I want you to go back and double check your math, but that should be the answer to the second question. Okay, so as always, please let me know if you guys have any questions, and I will see you guys in the next video.